So in this video we'll be learning two terms. One is numerical aperture and the other one is acceptance angle. So numerical aperture is nothing but the ability of an optical fiber to collect or confine the incident ray that is incident on it. So we all know that we are transmitting light through optical fiber. So in order to transmit that light through the optical fiber, we have to launch this light. Okay, so we'll be launching this light, but it is not necessary that all these lights should confine inside the fiber for it to propagate. So the ability of the fiber to confine all these rays that are coming in its way to its fiber axis or fiber so that it gets propagated. Okay, so that term which defines the angle in which a ray should be launched so that it gets propagated, or it get confined to the fiber and it gets propagated, that angle is called acceptance angle, and the area of curvature in which the ray should be launched so that it is confined to the fiber and finally it gets propagated through the principle of total internal reflection, that is called the numerical aperture. So this numerical aperture and acceptance angle are interlinked. Okay, now we'll see the derivation for numerical aperture. So deriving the term for numerical aperture will result in the derivation of the acceptance angle also. As I have already mentioned, numerical aperture and acceptance angle are interrelated. So now consider a ray Xa that is incident into the optical fiber with an angle alpha with the fiber axis, and the refractive index of the medium 1 is considered n. Usually the medium n is considered to be air, and the refractive index of the core is n1 and that of the cladding is n2. So for deriving the expression for numerical aperture, we'll be using the Snell's law for two cases between two mediums. First, it will be between the medium 1 and the core, that is the ray Xa. The ray Xa is incident on the fiber with the fiber axis at an angle alpha. That ray gets refracted with a angle theta with the fiber axis, that's a refracted ray. So we'll be applying Snell's law in this case. And secondly, this refracted ray again touches the core cladding interface. Here the medium 1 is the core medium and the medium 2 is the cladding medium, represented by the refractive index n1 and n2. And we'll be applying the Snell's law for this case also. Here the incident angle is theta c and the angle is considered to be the critical angle. So when a ray is incident on the core cladding interface at a critical angle theta c, the refracted ray surpasses the boundary of separation between the core and cladding, that is the refracted angle will be 90 degree, as you can see from the figure. So by using these two these two conditions, by applying Snell's law at these two boundaries, we will be explaining or deriving the expression for numerical aperture. So applying a Snell's law to the air core interface, we'll be getting the expression as n sine alpha is equal to n1 sine theta. That is, our Snell's law is n1 sine theta 1 is equal to n2 sine theta 2, where theta 1 and theta 2 are the incident angle and the refracted angle. Here our incident angle is alpha, or our acceptance angle, and our refracted angle is theta. Okay. So we got the expression as n sine alpha is equal to n1 sine theta. So considering a right triangle between the ray AB, the normal, and the fiber axis, we get a right angle triangle. From that, the value of theta can be expressed as pi by 2 minus theta c. Again, substituting here in the expression, n sine alpha is equal to n1 sine pi by 2 minus theta c. Sine of pi by 2 minus theta c is cos theta c. So rewriting the expression, we'll get n sine alpha is equal to n1 by n cos theta c. Again, we know that sine square theta plus cos square theta is 1. So from that we write out the expression for cos theta c. Writing that expression for cos theta c, we just write it on there, just mark it as equation 4. Now we'll apply the Snell's law to the core cladding interface. Here, the incident ray is AB and it is incident at an angle, critical angle theta c. So, the refracted ray surpasses the boundary between the core cladding interface and the refracted angle is 90 degree. Applying these to the Snell's equation, we'll get n1 sine theta z is equal to n2 sine 90 degree. Here our incident angle is theta c and the refracted angle is 90 degree. So again reducing, we'll get n1 is equal to sine theta z is equal to n2. We know the value of sine 90 is 1. Rewriting sine theta z is equal to n2 by n1. Now we will be substituting the above value in our equation 4. Okay, so our cos theta z will be equal to root of 1 minus n2 by n1 the whole square. We are substituting the value of sine theta z as n2 by n1. So here we are substituting the value of cos theta c in equation 3. We get sin alpha is equal to n1 by n root of 1 minus n2 square by n2 square by n1 square. Rearranging this, we can write sin alpha is equal to root of n1 square minus n2 square by n. Here n is the refractive index of air and we know that refractive index of air is 1. So we can substitute the value of n is equal to 1. Hence we get sin alpha is equal to root of n1 square minus n2 square. So this is called the numerical aperture. The numerical aperture NA is equal to square root of n1 square minus n2 square and the acceptance angle alpha is equal to sine inverse square root of n1 square minus n2 square. Why we are reducing like this? Because a numerical aperture and the acceptance angle are interrelated. So if you know the core refractive index of a core and if you know the refractive index of a cladding, you can find the numerical aperture. That is NA is equal to square root of n1 square minus n2 square, where n1 is refractive index of core and n2 is refractive index of the cladding. And you can also find the acceptance angle, that is alpha is sine inverse of square root of n1 square minus n2 square.